Hello guys, welcome to the Innovation Lab. In this video, we're going to be conducting a full test and review on this 3000 watt 24 volt pure sine wave inverter charger made by Sungold Power. So Sungold Power was also gracious enough to send us a 24 volt 100 ampere hour lithium iron phosphate battery system that we're going to be using to test the power inverter. So the plan is to focus this video on the power inverter, and in the next video we're going to be reviewing and testing the battery system. Alright guys, as you guys may have seen in our previous videos, we always add chapters to our videos to help you guys navigate the content and to also allow you to skip through the sections that you find more interesting. The plan is to shuffle things around a little bit to keep the video fun and interesting, to keep you guys engaged. And in some of the chapters, I'm really excited to show you guys the major components that is inside this pure sine wave inverter, and we're going to be conducting some load tests and efficiency tests to show you guys really how efficient this unit is. And lastly, I really plan to take this unit outside to show you guys the real application. I'm going to be using it to cut some wood and show you guys what you can actually use a complete system like this to do in real life. All right, my friends, let's jump into it. As you guys know, when working with battery systems, especially lithium phosphate battery systems that pack a lot of energy, high energy density, high power density, it is very important to make sure that you pay attention to what you're doing, make sure that you guys keep the area clean, and also pay attention to the polarity of both the battery system and the power inverter. As you guys can see here, everything is color coded. Red is positive, black is negative, and in the end we're going to make sure that we install the terminal covers to keep things safe. So one additional layer of safety that I add whenever I'm connecting power inverter terminals like this is I'd like to use an inrush control resistor to be able to charge up the input capacitance of the power inverter first, so that way we don't get an arc when we're connecting the terminals. Alright guys, for the initial power run test, given that we have connected everything, we have connected the power cables, we have covered all the terminals, the next thing we had to do was to measure the initial battery voltage that this battery came in at, and we saw a voltage measurement of 26.29 volts. So for the initial power run test load, we're going to use our 120 volts 300 watts incandescent light bulb, which is more like an AC resistive load, and all we had to do was to connect that load to the 120 volts AC power outlet that comes out of the power inverter. And after that, we turn on the system, and as you guys can see, this inverter does a very sweet and very nice soft start function, which is actually beautiful to watch, and in my opinion, depending on the load that you're driving, I think that's an amazing function. As you guys have seen, the power inverter came up really nicely and it drove the 300 watt load. And also looking at the oscilloscope, we see a very clean pure sine wave output coming out from this power inverter, even with the load applied. And looking at our measuring devices here, we can clearly see that this power inverter is obviously pulling greater than 300 watts of power from the battery system. And this is what we would expect, as we have to always account for the power inverter efficiency and power losses. Alright, so before we go into the load testing and conducting all the efficiency measurements, the first thing we needed to do was to look at the quiescent power or the idle power of the pure sine wave inverter. And what we saw was that at a battery input voltage of 26.63 volts, the inverter was drawing an input current of 2.34 amps. So that gave us a quiescent power of 62.3 watts. So in a nutshell, the quiescent power or the idle power is the amount of power that the pure sine wave inverter needs to get the internal components operational, and at the same time, even though we don't have a load applied at the output of the inverter, kind of kickstarts the low frequency power transformer inside the power inverter. And if you guys listen closely, you can kind of hear the transformer hum. So for the initial load test and efficiency measurements, so we're going to be using our DIY 5-channel AC load box, and this load box allows us to do a 300 watt load step. So all we had to do was to install a 300 watt load on each channel. We had the load box connected to the power inverter. So with all the test loads installed on the load box, all we had to do was to incrementally step in the load 300 watts at a time until we got to a total load of about 1600 watts. So looking at our DMMs here and our current probes, so what we saw was an overall input power coming in from the battery to the power inverter system of about 1867 watts, and an output power, when we do the math, we get to about 1594 watts. But also we have to account for a cable loss of about 20 watts, given that when we measured it, we saw a small voltage drop between the battery and the power inverter. So this power inverter gave us an efficiency of 86%. For the second test load, I wanted to see how this power inverter would respond to an inductive load, and for that we used it to drive our electric grinder. And what we're seeing is that there's a little bit of a harmonic distortion when the grinder starts up, but after that it was kind of smooth sailing, no issues at all, no distortion on the sine waves. And yeah, I think that is quite impressive. And even when we applied some load on the grinder by actually using it to do some cutting, the waveform stayed the same, no distortion. So I only saw the distortion when the grinder kicks in, and after that no issues at all. And finally, we also use this to drive an electric iron. So my goal is to use it to drive different kinds of loads to see how this power inverter is going to respond. So for that, we plugged in an electric iron and we allowed the iron to heat up a little bit, and we took our measurements. Looking at again our DMM and our current probes, we saw an input power going from the battery system to the power inverter system of about 1676 watts, and an output power going into the electric iron from the power inverter of about 1440 watts, which is very close to 1500 watts. The electric iron is actually rated for 1500 watts, so it was kind of pulling slightly less than that. And again, when we do the math, we saw that this inverter was giving us an efficiency of approximately 86%. This power inverter comes with a detailed product manual and specification sheet. To save some time, we're just going to focus on the core specs and details that you're supposed to know to be able to safely operate this power inverter. In a nutshell, this product is a 24 volt, 3000 watt pure sine wave power inverter and charger. The power inverter is rated for an input and output voltage of 120 volts, and this is an input and output rating because this inverter takes in AC input as well during the charging mode, or when you want to use it kind of as a UPS, and the battery charging system can deliver up to 40 amps of charge to your battery. This power inverter has a storage power rating of 9000 watts for 20 seconds. That means that it can withstand about 9000 watts of power within a brief period of about 20 seconds, and that's amazing. It has an AC output rating of 120 volts AC, an AC input voltage rating of 120 volts AC, and the output waveform is pure sine wave as we would expect. It has a maximum transfer time of 10 milliseconds. So what this means is that when you're transitioning from battery power to AC input power, you're switching your load from the power inverter to AC. It takes about 10 milliseconds max to make that switch. So that's why when we do the test, you guys will kind of see a flicker on the light bulb that we're using to simulate the load. So that's the 10 millisecond window when the power inverter is kind of processing what's going on and switching the power over. I'm seeing here on the spec sheet that it says that the nominal efficiency is greater than 88%, but actually on the user manual, what I saw was a peak efficiency of 88%. So this specific spec between the spec sheet and the user manual is a little bit conflicting the way it is kind of worded. So what I can say is that during the efficiency test, as you guys have seen, we measured steady efficiency of about 86% at about 1500 watts of load. So based on that, it's looking more like what they had in the user manual is more correct, of a peak efficiency of 88%. On the DC input side, the nominal input voltage is 24 volts and it has a minimum start voltage of 20 volts, a low battery alarm range of 19 to 20 volts, a low battery trip if you set it to switch 1 of 18 to 19 volts, a high voltage alarm of 32 volts, low battery voltage restart of 26 volts, idle consumption of 46 watts, and you guys will see this when we actually conduct the idle or quiescent power measurement, and a power saving mode consumption of 19 watts. Alright, there's a lot more specs here, but the key ones for the charging system is that it can deliver up to 40 amps plus or minus 5 amps. Also, one additional feature that came with this system is that it has a remote control module. It's not quite wireless. It has cables plugged to it, like long cables plugged to it, but still I think that's a very good thing to have. If you want to use this system to put it in an enclosure or put it in a place where you will not be able to access the actual inverter all the time, I think at that point that remote control module will come in handy for you. So some more details on the design features of this power inverter is that the design is actually considered the full bridge topology, and the charger uses an isolate boost topology. I think I kind of have an idea what that is supposed to do, but I am not 100%, so I'm not going to talk about it. So this power inverter has an average THD of about 10%. So THD, for those of us who are not familiar with the concept, stands for the total harmonic distortion on the sine wave. It's basically a representation of how much distortion we're getting on the sine wave, and you kind of see more of this kind of noise on the sine wave if you're driving a nonlinear inductive load. So if you're looking at the oscilloscope and your sine waves are very clean, THD is probably very low, and that's a very good thing. So kind of going through the user manual, I learned something about this converter that I didn't even know it could do that. The auto frequency adjustment. The power inverter is programmed to do either 50 Hz or 60 Hz. But they're saying that once you plug in an input power, the power inverter will kind of switch over to the frequency of the incoming power to kind of tell the inverter that this user's equipment is kind of set up for this frequency range that is coming in from the input power. And I think that's an amazing function. So one of the first things that you see on top of the power inverter as you look at it out of the box will be the battery type selector. The product manual lists out all the different kinds of batteries by number. So the one that is most relevant to us in this video is option number 7, which is for the lithium iron phosphate battery, which is exactly what we have that we're going to be using to drive this system. Alright guys, the last critical feature that I would like to go over in this review is the dip switch configuration that comes with the power inverter, and this can be found at the back of the power inverter. So each switch position kind of tells the inverter what to do in that mode. So you have switches 1 to 5. Switch 1 is the low battery trip voltage setting, and switch number 2 is the AC input voltage range. Switch number 3 is the power saver auto setting. Switch number 4 is operational frequency setting. Switch number 5 is the battery/AC priority. So this one is where you need to pay more attention if you want to use this power inverter either as a UPS or as a battery charger, because if you don't set this right, it's not going to work. So it's something I had to figure out during the testing. So setting it at position 1 or position 0 will tell the power inverter, should I prioritize the inverter function, which is converting battery to AC power, or should I prioritize the AC power coming in whenever I see an AC, kick off the inverter. That way we can save some power at the same time recharge the battery system. Alright guys, as I mentioned earlier, I just focused on the high level specs and the high level features, the high level functions. So one thing I would recommend is if you're thinking of getting this power inverter, the actual user manual is very well detailed. There's a lot of information packed in there. I will suggest that you take some time to go over that manual to know exactly how you're going to be implementing any function that you're thinking of using. For the battery charging and the UPS test, the first thing we had to do was to make sure that we connected an input power cable and an output power outlet to the power inverter, and following the labeled terminals on the inverter, we just had to make sure that we match the color convention just to ensure that we connect the AC wires to the right terminals. And as you guys can see here, we broke out the wires that came out of the power cable. The green wire is going to be for the ground terminal. the black wire is going to go to the live and the white wire is going to go to the neutral. And we're going to follow the same exact configuration for the power outlet that we're going to use for the UBS testing. Alright, so with all the power cables properly configured, the next thing we had to do was essentially to plug in the power inverter to an input voltage of 120 volts AC. Also, one thing I realized looking at the manual was that for either the battery charging or the UPS to function properly, you have to make sure that you configure the dip switches in the back of the inverter to kind of recognize the operational state of the converter that you're going to be using it for charging and also to be driving an uninterruptible load. Alright, so with all the configurations that we just talked about completed, the battery is connected and we have turned on the AC power coming into the pure sine wave inverter. So now we're using the inverter as a charger. All we had to do was to slowly increase the charging current adjustment on the power inverter. We saw a charging voltage of 27.24 volts at a charging current of 36.2 amps. So when you do the math, we were seeing that this power inverter was delivering a charging power of about 986 watts, which is impressive. So at this charge rate, considering the battery capacity that we're working with, so it will take this charger about 2.5 hours to fully recharge this battery system. And in my opinion, I think that's impressive. Also, another thing that we did was use our oscilloscope to keep an eye on the ripple voltage going into the battery during the charge phase. And what we saw was an RMS ripple of less than 300 millivolts. So considering the charging voltage level, 300 millivolts of RMS ripple translates to about 1% ripple overall. And in my opinion, I think that's good. The next test we conducted was the UPS system, which is the uninterruptible power supply system. The only thing is that in the manual for this inverter, there is a transfer time of 10 milliseconds. So if you have a load that is that sensitive to 10 milliseconds, this function is not going to work for you. But I believe that for most loads, especially loads that are slightly capacitive, 10 milliseconds should be fast enough to where you can use this power inverter to provide uninterruptible power to those devices. As we talked about earlier, we had to make sure that we have the cable that brought in the input power and the outlet that we're going to plug the load into to maintain that uninterruptible power handshake between this power inverter and the AC that is coming in. And also remember that we had to configure the dip switches in the back of the converter, especially switch number 5. We had to set that to position 0, which is a utility priority. So as you guys can see, so this is kind of a visual test and a time test. So whenever there is a power handshake, so you guys can almost see the 10 millisecond flicker on our load. Also for this function, there is a 15-second delay for AC power coming in. So this essentially means that every time there is a reset or restart of the input AC power that is coming in, so the power inverter knows to wait for 15 seconds before it switches the load to the input AC power that is coming in. Alright guys, one of the things that I wanted to do in this video is to show you guys the real life application of what you can do with a power system like this. And given that we have both the battery system and the power inverter system, and honestly this review couldn't have come at a better time because I'm currently doing some home improvement project. So essentially what I did was to hook up the system in my backyard, and as I am doing some work there, so I'm gonna be using it to cut up some wood, some pallets that I'm looking to dispose using a few different kinds of saws that I have here, some table saws and all of that. Yeah, so in a nutshell, let's just take some time to observe the performance of this system. I know that a lot of you guys are very curious, just like myself, and we would like to know what's actually inside this pure sine wave power inverter. Alright guys, so let's go ahead and look at the major components that can be found inside the Sungold pure sine wave power inverter. So the goal is to do this as non-invasive as we can. Removing the top cover of the inverter to take a peek at the inside is the most invasive we're gonna get with this process. So the idea is to show you guys the high-level components that is used to design this awesome product. Alright, so let's take a closer look. So going from the rear to the front, we have these two massive terminal lugs here, or connectors here. You have the negative and the positive. You can also see the fan there. And now looking at the actual inside of the pure sine wave power inverter. So the major components, I would like to break them down to the level of the control board that we see here. We have the power board down here. And we have the power transformer. So this is a low frequency soft iron core power transformer. I'm not 100% sure, but I believe that this should be some kind of a full wave transformer or configuration. And looking from this direction, you guys can kind of see the fan that cools the unit in there. We have this very nicely connected bus bars here that bring in the positive to this heatsink here, and we have another bus bar that brings in the negative onto the system here. I believe it is supposed to interface with the control board. Unfortunately, we're not going to be able to peek into that. And over here we have two circuit breakers and we have power outlets down in here, and that is pretty much it. And looking closer at the control board, this is where, as you guys can see here, what looks like a microprocessor or microcontroller that controls the unit. We have a bunch of integrated circuits in here. We have all these awesome relays and capacitors. The buzzer is actually what gives us all kinds of audible signals for or when the power inverter is switching between operational modes or states. So the power board or power switching section here, as you guys can see, there's a whole lot of MOSFETs here. So what I've seen so far is about 3 heat sinks on this design. The first heat sink here, and there are 2 more heat sinks in the back, and all of them have like MOSFETs mounted to them. So this is quite impressive. This is amazing. A whole lot of MOSFETs that drives the system is mounted on those heat sinks, and they all interface with the power board here. Also in here on the power board, right in the middle, unfortunately, we're not going to be able to see those very clearly. There are some electrolytic caps on the power board, which I think is awesome. Very nicely placed between the heat sinks on this board, and I believe those should be used for as input filter caps. I fully understand the design topology, but I'm not going to be able to go into the details because this is not my design, and the goal for doing this is only to give you guys an appreciation of the internal design, internal components that make up this awesome pure sine wave inverter. And lastly, on the control board, we have a few connectors here that interface with the control modules that are mounted on the enclosure, and those control modules are what allows the user to be able to configure the power inverter towards what they want it to do, and they also serve as an output to the user, and this allows the user to know what the power inverter is doing. Alright guys, that's really it for this video. As you guys have seen in the video, the design of this power inverter is actually awesome. The power inverter performed really well, and we used it to conduct all kinds of tests, and we used it to have some fun doing some home improvement project. And I'm really excited and looking forward to all the experiments that we're going to be conducting on this system. And if you like to see all of that, don't forget to subscribe to the Innovation Lab so you get notified as we are releasing all those videos. Alright guys, and lastly, let's talk about some design improvements from my standpoint, just my opinion. So the first thing that comes to mind is the power inverter efficiency. While I fully agree that 88% is very good for a low frequency pure sine wave power inverter of this nature. It will also be good if there's some tweaks that could be done on the design to improve that efficiency by just a little bit, because if you think in terms of power losses, consider a situation where the user is driving this power inverter right at 3000 watts. If you do the math, right at 88% efficiency, you're going to be losing about 360 watts if my math is correct. Again, in my opinion, these efficiencies are already good. I'm just saying that whatever can be done to tweak them a little bit, make them better, would be awesome. So another thing that comes to mind is the price of the product. So anything that Sungold Power could possibly do to lower the price of this power inverter just a little bit, to make it more affordable for our audience, maybe some discounts, maybe some design packages with less accessories like the remote control or something like that to lower the costs, that would be great. The last thing that comes to mind is for Sungold Power to ensure that when they ship the unit, they ship it with the power cables. Because when you don't do that, the end user may use the wrong wire gauge, and by wrong I mean smaller gauge wire, and that will greatly impact the performance of the pure sine wave inverter. So for me, it took me a while. I had to go to some local hardware stores to find some cables, but when I found them, they were kind of slightly longer than I would have preferred. I'm sure that would have had some small impact on the performance of the converter, efficiency wise. Alright guys, I want to thank you guys for watching this video and being such an awesome audience, and I'm looking forward to all the wonderful experiments and projects and things that I'm going to be doing with this system, since Sungold Power sent us the inverter with the battery system. So in a nutshell, we have everything we need. So we're going to be conducting a whole slew of experiments and tests with this system, and if you would like to see that, don't forget to subscribe to the Innovation Lab. Alright guys, I hope you had some fun watching this video, and if you did, don't forget to give us a thumbs up. Don't forget to subscribe. Alright my friends, I will see you guys in the next video.